Okay. Yeah, thank you for your kind introduction. First of all, I would like to thank Professor Nalim for inviting me to give a talk at this conference. Yeah, and I'm happy to meet some of my friends, like Kamani. Yeah, he came to Taiwan once, right? Yeah. Okay. So today I'm going to talk about pulping materials for and regional design of pulpings for solar cells. Yeah, there are a number of emerging solar cells. My group has been working on the synthesis of pulverins material for application in dye-sensitized organic and perovskite solar cells. And this is the latest cell efficiency chart reported by NREL. The highest certified efficiency for DSC is 19.9%. and 16.5% for organic solar cell, and 25.2% for perovskite cells. Oh. Okay, and this figure shows the working principle of a DSC. The system is composed of a dye bound to the surface of titanium dioxide and electrolyte and counter-electrode. Photo excitation of the dye results in electron injection to the conduction band of titanium dioxide, and then the electron goes through the external circuit to the counter-electrode. And dye regeneration is achieved by reduction with the redox mediator. To increase the cell performance, and we need to suppress the decay process of the excited dye to the ground state, and also reduce charge recombination of the titanium dioxide electron to either oxidized dye or electrified. Okay. So as you can see, the structure of DSC is simple. So DSC may become a low-cost alternative to conventional solar cell. Okay, good. Yeah, the breakthrough work by Grazo and co-workers show the family of ruthenium dye, such as N3, N719, and black dye, achieved a power conversion efficiency of around 11%. And so to improve the cell performance of DSC, numerous ruthenium dyes based on the structure of N3 dye have been developed. For example, Wu showed that incorporation of diethylene to the bipyridine ligand increased the cell performance of the DSC. And similarly, Wang reported an efficient dye C106, and the cell performance is 11.7%. The fundamental limitations of ruthenium dyes have encouraged the exploration of cheaper and safer organic dyes. Metal-free organic dyes have a number of advantages, such as facial modification of the molecular structure, low production cost, high extinction coefficient, and no resource limitations. And the disadvantages of organic dyes are narrow absorption bands, molecular aggregation, and lower stability as compared to ruthenium dyes. Okay, in the last 2 decades, a large number of organic dyes have been synthesized, but only limited examples of organic dye that shows comparable efficiency with the ruthenium dyes. So how do we find the best performing dye? And the answer may come from nature. We all know that nature is much smarter than human beings. Nature has been using sunlight to do photosynthesis for billions of years. In the photosynthetic plants or bacteria, sunlight is collected by chlorophylls to convert solar energy to chemical energy, which is a complicated process. And this figure shows the active site of photosynthetic bacteria. The where like chlorophyll arrays play an essential role in efficient light harvesting, energy, and electron transfer. And inspired by the efficient photosynthesis performed by plants, numerous porphyrin dyes has been synthesized and used in DSC. And here's a structure of some chlorophylls. The first example of porphyrin sensitizers in DSC was reported in 1993, and the free-base zinc and copper complexes of beta substituted chlorophyll derivatives and related natural porphyrin were tested, and in this series, the best performing porphyrin shows an efficiency of only 2.6%. In the last 2 decades, a lot of porphyrin dyes have been prepared for DSC. In 2007, Officer and Grazo reported a series of green porphyrin dyes with a carboxyl group connected via the beta position. Before 2010, they were the most efficient porphyrin dyes, and the energy conversion efficiencies are in the range 5.1 to 7.1%. At the time we started to work on porphyrin-based DSC, there's no guideline of molecular design for high efficiency porphyrins. So we made a series of porphyrins with a variety of molecular structures, and we found these 2 types of porphyrins with push-pull framework. And in type 1, there's a donor directly attached to the meso position, and in type 2, there's a carbon-carbon triple bond between the donor and the porphyrin ring. Based on the push-pull framework of YD1, we designed and synthesized the second generation of porphyrin dyes. In YD2, hexyl group were used instead of terbutyl to reduce molecular aggregation. And to increase the electron donating ability, epoxyl groups were used for YD3 and YD4. And the electron donating effects are even stronger for this triamine. And YD6 to YD8 with triphenylmine were also prepared for comparison. So with these porphyrins, we were able to study how the nature of the push unit influences the cell performance. Among these porphyrins, YD1 to YD4 show higher power conversion efficiency than the reference YD0. And the triphenylmine substitute porphyrin shows comparable efficiency with the reference. And then the efficiency of triamine substitute porphyrin YD5 is poor. And this is the energy level diagram of porphyrin YD0 to YD8. The energy levels for these porphyrins all meet the requirement for effective electron injection and dye regeneration. Also, YD3 and YD4 have a epoxyl group on the diphenylmine. The additional electron donating group did not improve the cell performance, and this may be because the additional electron donating group raise the energy level of the HOMO so that dye regeneration becomes lower. And such an effect is more pronounced for YD5, which has a more even stronger electron donating group, triamine. So how do we improve the cell performance of the dyes? And we know the overall power conversion efficiency is a product of photocurrent, photovoltage, and fill factor. And the fill factor is related to the resistance of the device. From the viewpoint of the molecular design, there's not much room for improvement of the field factor. So optimization of the field factor is not considered. The most straightforward way to improve the cell performance is to increase the photocurrent, and this can be achieved by making the absorption of the dye rate shifted. Suppose the VOC and field factor remain the same, okay, and if the absorption is rate shifted by 50 nanometer, the overall efficiency may increase like 1 to 2%. So to increase the light harvesting ability of porphyrins, we need to know the origin of the absorption spectrum of porphyrins. The absorption spectrum of a typical porphyrin, such as zinc OEP, shows a strong solar and moderate Q bands, as used in here. And this can be explained by glutamine 4-orbital model. And EGX and EGY are degenerate, and A1U and A2U are close in energy. There are two transitions, A1U to EG and A2U to EG. Configuration mixing of these two transitions results in strong solar and moderate Q bands. Unsymmetrical extension of pi conjugation causes splitting of pi and pi star levels and decrease in the HOMO-LUMO energy gap, leading to broadening and rate shift of absorption and increased Q band relative to that of solar band. In such a case, the light harvesting property is enhanced. So YD2 is based on a push-pull structure. So to increase the unsymmetrical extension of the pi system, we put more than one donor to the porphyrin. And additional diphenol or triphenol at the meso position cause rate shift and broadening of the absorption. The simulated spectra are consistent with the experimental ones. The donors are diphenol or triphenol units. However, introduction of more than one donors to the meso position of porphyrin dyes did not improve the cell performance. To further extend the pi system and improve the light harvesting efficiency of porphyrins, we made these porphyrins porphyrin dimers YDD0 to YDD3 with varied connectivity between porphyrin rings. The two porphyrin rings are connected by an acetylene bridge for YDD0, and the two porphyrin rings are directly connected at a meso position. And for YDD2 and YDD3, the porphyrin rings are fused. All these porphyrin dimers show much broader absorption than the reference YD0 because of exciton coupling, electronic coupling, or extension of the pi conjugation. Some of them show absorption more than over 1,000 nanometer. Porphyrin dimer YDD1. This YDD1 performs better than the reference YD0. And in the IPC spectrum, as you can see, the dip between solar and Q band is filled up for YDD1. And YDD0 shows IPCE spectrum extending over 800 nanometer, although the IPC values are only 30 to 40%. And a small response was observed for dimer YDD3, and essentially no response was observed for YDD2. So the lower efficiency for dimer YDD0 as compared to the reference is due to die aggregation and also decreased LUMO energy level, which may impede electron injection from injection to titanium dioxide. And the LUMOS for fused porphyrins is insufficient for effective electron injection to the titanium dioxide. We also made push-pull porphyrin dimers, YDD4 and YDD5, with a diphenylamine attached to the meso position. Dimer YDD5 shows slightly better efficiency than YD2 for thin film samples because YDD5 has better light harvesting property. Under optimized conditions carried out in Professor Grezzo's group, YDD5 achieves an efficiency of 9.6%. Among all the porphyrins mentioned above, the most efficient porphyrin is this YD2. And as you can see, the IPC values extend over the whole visible region and the near IR region, giving a large photocurrent. And the PCE is around 11%, which is comparable with the most efficient ruthenium dyes. So we next try to modify the molecular structure based on YD2 with the aims of improving the light harvesting capability. In other words, achieving redshifted and broadened absorption. At the same time, we have to reduce die aggregation and charge recombination rate, and also increase the long-term stability. So we modify the donor, mesophenol, and the acceptor. Here's a structure of YD2. The terbutyl group at the meta position of the phenol are not bulky enough to completely suppress die aggregation. In YD2OCA, the long axial chain at the also position of the mesophenol can reduce die aggregation, and also the hydrophobic environment can block the approach of the electrolyte to the surface of titanium dioxide to reduce charge recombination, thus enhancing the VOC and PCE. Using cobalt-2, cobalt-3 as the electrolyte, the YD2OCA device achieves an efficiency of 11.9% when co-sensitized with this organic dye Y123. The device achieves an efficiency of 12.3% under 1 sun illumination and 13.1% for 50% sun illumination. As you can see, the VOC for YD2OCA is much higher than that of YD2 because of the hydrophobic axial group can reduce charge recombination rate. In 2011, YD2OCA made a new record. Our porphyrin GY50 with the benzosyldiazole inserted between phenolene and acetylene achieves an efficiency of 12.75%, which is even better than YD2OCA. In contrast, GY21 with the carboxy directly attached to benzosyldiazole shows much lower photocurrent and photovoltage because of much faster charge recombination as compared to GY50. Recently, Kim's group reported tandem DSC, which is composed of SGT137 top cell and SGT021 bottom cell, and the device shows an efficiency of 14.64%. As you can see, the structure of SGT021 is similar to our porphyrin YD2OCA and GY50. And they use a bulkier donor. We also modify the push-pull and mesophenols for YD7OCA system. And I don't like to go into detail for this system because of time limit. The best performing Prof in this series achieves an efficiency of 10.3 using iodide, triiodide as the electrolyte. Yeah, as mentioned, the overall PCE of DSC is a product of JSC, VOC, and fill factor. In addition to increasing the photocurrent, we can also increase the VOC if we use electrolyte with a more positive redox potential. To that, the most efficient DSC have been achieved using cobalt-based electrolyte in combination with porphyrin or organic dyes. And recently, copper electrolytes have been used in DSC because of their more positive redox potential, so that you can get a higher VOC. And the reorganization for cobalt electrolyte is also less than copper electrolyte. In the devices, terbutylpyridine is generally used as additive to upshift the conduction band of titanium dioxide and also reduce charge recombination. However, the addition of terbutylpyridine in DSC, the terbutylpyridine reacts with cobalt electrolyte. For example, Hammond's group showed that the presence of TBP additive will coordinate to the copper center and then displace the bidentate ligand. And the reaction of TBP with copper electrolyte will change the redox potential of the copper electrolyte and influence the cell performance and also the long-term stability of the devices. And in the case of copper DMP2, we found TBP coordinate to copper center, but did not displace the bidentate ligand DMP. And we found there are two newly formed species after 2 days later. And it's interesting that the JSC and VOC drop only 5 to 10% after 46 days. And the fill factor drops a lot because of the poison of the platinum electrolyte. So we need to improve the stability of the counter electrode and develop new materials for copper electrolyte for long-term stability. So as you know, indoor light harvesting is becoming more and more important. DSC are superior than other types of photovoltaic technology. The photon flux under indoor environment ranges between around 200 to 3,000 lux. The Y1A1 porphyrin shows a power conversion efficiency of 9.22 under one sun condition, and it shows good absorption in the visible region and nice spectra match with the artificial light source such as LED T5 in the range 400 to 500 nanometer, and partial spectral overlap in the red region. Under 350 lux of LED light, the device shows an efficiency of 19.5%. The cell performance of our dye TY6 is even better, and it shows an efficiency of 28% at 6,000 lux, which is much better than the reference N719. Also, the cell performance of N719 is higher than TY6 under one sun condition. We are also interested in porphyrin-based organic solar cell. There are a number of device structures for organic solar cell. Here are two representative structures: bilayer heterojunction and bulk heterojunction. When a donor molecule absorbs light, the electron is pumped from the HOMO to the LUMO, and then the electron goes to the LUMO of the acceptor and then to the cathode to generate photocurrent. Up to date, this series of porphyrins reported by Penn's group are the best performing dyes for porphyrin-based organic solar cell. In the molecules, two diketoprolol are used to attach to a porphyrin via acetylene bridges. The conjugation between the porphyrin and the acceptor results in broadening and redshift of the absorption. So in the OPV project, we started with simple porphyrin without any acceptors attached to the porphyrin. At the very beginning, we would like to know porphyrin, single porphyrin or dimeric porphyrin works better. So we made these three dyes, KC0, KC1, and KC2. And as expected, the dimer KC1 and KC2 show much broader absorption than the reference KC0 because of strong electronic coupling between the porphyrin units mediated by acetylene or a butyl-ion bridge. And in these three porphyrin dyes, dimers KC1 and KC2 shows better efficiency than single porphyrin KC0, probably due to higher light harvesting capability for dimers. And this is the surface morphology measured by FM. As you can see, KC1 brand film shows a connection of grains, whereas KC2 shows is relatively homogeneous. So the KC2 gives higher hole mobility and photocurrent. The cell performance of KC2 can be improved by addition of chlorolaphthalene. Later, we use DEPCO to trigger the supermolecular assembly of KC2, forming KC2 duplex. The TEM image of KC2 PCBM films show relatively larger phase separation, whereas KC2 duplex PCBM CN shows better donor acceptor mixing, and so the PC is higher for KC2 duplex PCBM CN. So currently we are trying to put a variety of acceptors to the porphyrin, dimers or even trimers. And we recently developed a new donor and acceptor for small molecule organic solar cell. The device shows broad IPC spectra covering the visible and near IR region, and with fair IPC values, and a decrease of the amount of the acceptor results in increase in the PC. The optimized ratio of D1 and A1 gives a PCE of 7.21% for the best performing device. And perovskite solar cells have attracted much attention due to their low production cost, ease of fabrication, and high power conversion efficiency. In general, there are three types of device structures: conventional, inverted planar, and mesoporous perovskite cell. And in recent years, we have seen the efficiency for perovskite solar cell rises from 5 porphyrin. As you can see, there are 4 meso positions and 8 beta positions for molecular modification. So the electrochemical and photochemical property can be easily tuned. So some questions are raised. Porphyrins show very good light harvesting property. Will porphyrins decrease the efficiency of perovskite solar cell? And can porphyrins carry holes efficiently? So we start with the simple porphyrins. And HY1 and WT2 have a symmetrical structure, and HY2 and HY3 has a donor pi acceptor structure. As you can see, the HOMO energy levels of all these porphyrins are slightly higher than that of perovskite HOMO, which is good for electron transfer from porphyrins to perovskite layer. And compared to reference spiral meta, this HY series hot transporting materials show slightly lower efficiency. However, the dopant-free device drops a little bit, and the efficiency is around 13%. And we also make these porphyrins with 2 phenol groups at a meso position. Y2 has a symmetrical structure, and WT4 to WT9 have a donor pi acceptor structure, and the use of methoxy group and a phenol group is to fine-tune the energy level of HOMO. Among these porphyrins, Y2 shows the best cell performance, which is slightly lower than the reference spiral meta. And the device is composed of a perovskite layer spin-coated on titanium dioxide and a porphyrin hot transporting layer. The thin film sample perovskite shows broad absorption covering the UV and visible region. And in the presence of Y2, the black spectra is similar to the one without porphyrin. And the device using Y2 hot transporting material showed a PC of 6.6%, which is comparable to spiral meta with a PC of 18. And this is the best performing porphyrin based material at the time we publish the results. And we next try to modify the molecular structure based on Y2 to improve the performance of porphyrin hot transporting materials. A viable approach is to optimize the intermolecular interaction between porphyrin molecules to optimize hot mobility. So we design and synthesize these highly conjugated porphyrin dimers as hot transporting material. These dimers show slightly upshifted HOMO energy level, and the device is composed of FTO and compact titanium dioxide, mesoporous titanium dioxide, perovskite, porphyrin dimer, and gold. This is the SEM image of perovskite, and the right one is spiral meta. And as you can see, WT3 and YR3 shows uniform, complete coverage and pinhole-free surface covering on the perovskite layer. Here are the IV curves and IPC spectra. All these hot transporting materials show IPC values higher than 80% over the visible region. Among these materials, WT3 shows the best performance, giving a power conversion efficiency of 19.44%, which is better than the reference Y2 and spiral meta. we did a stability test for our device, and WT3 displays good stability, and it remains more than 90% of initial PCE after 800 hours. And in contrast, a dramatic drop down to 80% for the spiral meta device after 200 hours. So we also did the contact angle. We also studied the hydrophobic property of the hot transporting materials using contact angle method. The contact angle between the hot transporting material and water are shown here. Yeah, for the spiral is 65 degree, and Y2 81 degree, YR3 90 degree, and WT3 103 degree. So it should be noted the hydrophobic property for WT3 is large, and this is why the device based on WT3 is more stable than other hot transporting material, because the hydrophobic property of WT3 can provide better protection of the perovskite layer from the moisture in air, leading to better stability. Also, I'd like to make a conclusion. We have made a series of push-pull porphyrins, and we found bulky donor and long acyl chains and the mesophenols can improve the VOC and also the power conversion efficiency. And we found porphyrins can be used as hot transporting materials for high efficiency perovskite cell. And in the OPV project, we found ligand mediated assembly is a good method to increase the molecular size and improve the molecular orientation, and also extend the conjugation length. Okay, at last, I would like to thank my collaborators, especially Professor Guizzo, Xu, Diao, Wei, and Chen. My group worked on the synthesis of porphyrins, and my collaborators worked on the fabrication of device and all the measurements of the photovoltaic properties. And I also like to thank my students for their hard work. And I also like to thank the financial support from MOST and NCHU of Taiwan. And thank you for your attention.